forces on Earth, the ones that shape our weather. And we're starting this investigation with something invisible, fundamental, and shockingly powerful: pressure.
That's our mission for this deep dive. We're going to trace the path of a single concept, pressure, and show how it scales up from an everyday annoyance like, carrying a heavy bag, all the way to an atmospheric monster like a cyclone.
Right.
We're going to give you the physics behind the headlines, answering questions like, how does the weight of the air above us not crush our bodies?
Which is a great question.
And what's the mechanism that turns a simple wind pattern into a lethal spinning storm?
Okay, let's unpack this. We have to begin with the foundation that underpins, well, literally everything we're talking about today, whether it's solids, liquids, or gases.
Pressure is force divided by area.
PP, it seems so simple, but it's constantly at work explaining really surprising things in our environment.
The core insight there is proportionality. If you keep the total force, the total weight exactly the same, reducing the area dramatically increases the pressure. It's an inverse relationship.
And the sources gave us the perfect relatable example for this, the story of Megha and her brother Pawan carrying identical, really heavy backpacks. Pawan was miserable because his bag had these narrow, thin straps just digging into his shoulders, but Megha, with her bag, which had much broader straps, was perfectly comfortable.
And that's pure physics. The total downward force, the weight of the bag, was the same for both of them. But Pawan's narrow straps concentrated all that force onto a tiny surface area on his shoulder.
And that high pressure is what caused the pain.
That's what hurts.
Oh.
But Megha's broad straps took that exact same force and just spread it out over a much larger area of contact.
So the pressure goes way down, making the load feel much more manageable. The physics didn't change the weight, it just changed the distribution.
And that principle is exactly why a sharp knife cuts an apple more easily than a blunt one, or why you hammer the pointed end of a nail. You want maximum pressure for penetration, so you minimize the area.
Now, if we define this scientifically, the standard unit for pressure is the Newton per square meter, NM-WAC, which we usually just call a Pascal or Pa.
Right. And we use that same force over area relationship to engineer things not just with solids, but with massive volumes of liquids.
And that's where things get interesting, because liquids behave a bit differently than solids when it comes to pressure.
They do. The key principle with a liquid is that the pressure it exerts depends primarily on the height of the liquid column above where you're measuring. It's not about the total volume in the tank.
I remember the example from the source material comparing two pipes of different diameters, one narrow, one wide, but both filled to the exact same height with a balloon on the bottom of each.
Yes. And if pressure only depended on volume, the wide pipe should exert much more force, right? It holds more water.
Sure, it's heavier.
But the experiment shows the balloons bulge to the exact same extent. It proves that equal heights produce equal pressure, regardless of the overall amount of water.
So when we see water tanks placed high up on towers or rooftops, that's not just for storage. It's a deliberate engineering choice.
Absolutely. Placing the tank up high just increases the water column above your tap. That column height dictates the pressure, and that's what ensures you get a good, strong stream of water.
And if that height principle is true, then how does it apply to something enormous like a dam? The base of a massive dam is always, many times thicker than the top. Why is that?
Because that pressure dependence on depth is just taken to the extreme. The deeper the water, the greater the pressure it exerts horizontally on the walls.
Pushing outwards.
Exactly, pushing outwards. Near the bottom, where the water column is highest, the force is just immense. So to counteract that, engineers have to increase the area of the base dramatically. It's a fundamental solution to an extreme pressure problem.
It's all about balancing forces. Okay, so let's move from water to the invisible stuff that surrounds us. Air. The atmosphere. This is where the scale of these forces gets, mind-boggling. We don't feel the air, yet it's constantly exerting monumental force on us.
It is monumental. The atmosphere extends for dozens of kilometers above us, and that entire column of air has mass. The source material gives a startling detail.
Yeah.
The force exerted by the air column over a small area, say 15 by 15 centimeters, about the size of your hand, is nearly equal to the force of gravity on an object weighing 225 kilograms.
225 kilograms? That sounds like we should be flattened.
It does. That's 2,250 newtons of force constantly pressing on that tiny area.
So why aren't we? How is it possible that we're just walking around fine under the pressure equivalent of a 225 kilogram weight all day, every day?
That is the ultimate aha moment of atmospheric pressure. We aren't crushed because of a perfect internal counterforce. Our bodies that contain fluids and gases, our blood, our tissues that exert an internal body pressure.
And it's equal to the outside pressure.
It's equal to, and it balances the atmospheric pressure outside. It's a perfect equilibrium.
So if that balance is so perfect, is that what's happening when we fly at high altitude and our ears pop? The external pressure is changing, right?
That's precisely it. When you ascend quickly, the external pressure drops, but your internal pressure, especially the gases trapped in your ears, doesn't equalize instantly. That slight imbalance is what causes your ears to pop until your body can adjust and reestablish that crucial equilibrium.
That makes perfect sense. And for a visual demonstration of how powerful that external pressure is, we can just think about a simple rubber sucker.
The best everyday example. When you press that rubber sucker firmly onto a smooth surface, what are you actually doing? You're physically pushing most of the air out from underneath it.
So you're creating a little low pressure zone.
You're reducing the internal pressure dramatically. So now the pressure inside is extremely low, and the external atmospheric pressure, that 225 kilogram equivalent force, is much, much higher. That weight of the world is what presses down and holds it firmly in place.
So the sucker isn't sticking at all. It's being held captive by the weight of the air column above it.
Exactly. The force you need to pull it off has to be strong enough to overcome that massive pressure difference.
Now, when meteorologists talk about this, they don't usually use pascals.
No, for air pressure, the practical units are millibars, or mtecopounds, and hectopascals, HPA. They're both equal to 100 pascals. These are the units that define our weather.
Right. They tell us the difference between a high-pressure system and a low-pressure system.
And that pressure differential is the ultimate engine of wind. If air can move freely, it will always rush from a region of high pressure to a region of low pressure. It's always trying to achieve equilibrium.
This is critical, and it leads to an insight that seems a little counterintuitive at first. High-speed wind actually results in lower air pressure.
It does, and the sources described a great little experiment with 2 hanging balloons to show this.
Right, so if you hang 2 balloons a few inches apart and you blow air really strongly into the narrow space between them, what should you expect to happen?
Intuitively, you'd think you'd push them apart. But you'll see the opposite. The balloons actually move toward each other.
Why?
Because the high-speed air you blew in the middle created a zone of lowered pressure. The surrounding air, which is still, is at a higher pressure, and it physically pushes the balloons inward toward that low-pressure zone.
The faster the wind moves, the lower the pressure gets.
Exactly. So if we scale that principle up globally, wind circulation happens because of the uneven heating of the Earth's surface.
Right.
When land or ocean gets heated, the warm air above it is lighter, so it rises. As it rises, it leaves behind a region of low pressure on the surface.
And something has to fill that gap.
And cooler, denser air from surrounding high-pressure regions rushes in to fill that vacuum. This constant global process is what generates wind circulation across the planet.
And when you introduce moisture into that system of rising warm air, that's when you start to build the conditions for severe storms. What happens when that warm, moist air gets high enough that the water vapor starts to condense and freeze?
That is the birthplace of thunderstorms and lightning. You get strong upward drafts of warm air colliding violently with strong downward drafts of cooler air. This collision is happening between rising ice particles and falling water droplets.
And friction. Friction generates static electricity.
Precisely. This friction causes static electric charges to develop and separate inside the cloud. The lighter, positively charged particles get carried up toward the cloud top, while the heavier, negatively charged droplets settle in the lower part.
You get this huge charge separation.
Across vast scales, sometimes hundreds of meters. And when that separation, the voltage becomes too massive, the air, which is normally a brilliant electrical insulator, it just fails.
It breaks down.
It breaks down. And you get a sudden, explosive flow of charges that can move at speeds of up to 220,000 kilometers per hour. That is the flash of light we call lightning.
And the thunder?
That discharge instantly heats the surrounding air to temperatures hotter than the surface of the sun, causing the air to expand violently. That produces the intense, rapidly expanding sound wave we call thunder.
It's a truly startling force. And the sources point out that while the global pressure differential sets the stage, it's the localized geography and moisture that give these storms their unique, powerful regional identities.
That's a great way to put it. We see this acutely in regions like India. These localized thunderstorms have specialized names based on their vital agricultural role. They're known as Cowboy Shaki in West Bengal or Bordeauxle in Assam.
And they're crucial for crops.
They deliver essential water for Kharif crops right before the main monsoon. Or down south, you have the mango showers in Kerala and Karnataka.
Right, which helps the mangoes.
Exactly. They're destructive, sure, but they're also essential for the ripening of mangoes and the growth of coffee plants. So these events are absolutely critical to the ecosystem.
Now, if you find yourself caught in one of these storms, what are the critical precautions to keep in mind about lightning?
Safety is paramount. It is much safer to be inside a bus or a car than outside. You should immediately avoid tall objects like trees or towers and metallic objects. That includes metallic umbrellas.
And if you're stuck outside?
If you can't find shelter, you need to find a low-lying open area and crouch down low to the ground. Minimize your contact area. And critically, do not lie down flat.
Okay, let's transition from the thunderstorm to the largest, most destructive form of weather driven by this pressure differential, the cyclone. How does that initial rise of warm, moist air escalate into a spinning monster?
The crucial engine for a cyclone is a large body of warm ocean water. As the warm, moist air rises from the heated surface, the water vapor in it condenses. Now here is the positive feedback loop.
The storm feeds itself.
It does. When that water vapor condenses, it releases a massive amount of what we call latent heat back into the atmosphere. This newly released heat causes the air to rise even further, which creates an even lower pressure core at the center.
So more air rushes in even faster.
Exactly. The system is basically designed to spiral out of control.
And what turns that rushing air into a massive spinning vortex instead of just a straight line of wind?
That's where the Earth's rotation is vital. Specifically, the Coriolis effect. Because the Earth is spinning, air rushing from higher latitudes toward that low-pressure center is constantly deflected.
And that deflection gives it the spin.
It imparts this spin. This creates a massive, rotating system of high-speed winds and cloud bands. And at the very center of all this chaos, you find the most unique feature, the lowest pressure point, which is the eye of the cyclone.
And paradoxically, the eye, the center of the lowest pressure, is the calmest part of the entire storm.
It is. The winds are light. The skies can even clear up for a bit. It's a sharp contrast to the region immediately surrounding it, where you have the most intense winds and torrential rainfall.
And of course, without that constant supply of warm, moist air from the ocean, the cyclone loses its engine.
It gradually decays when it hits land, but not before delivering a catastrophic impact. The sources mentioned Cyclone Amphan in 2020, where peak wind speeds hit 270 kilometers per hour.
Yeah.
Just try to imagine the force of that.
And beyond the wind, the secondary effects are often even more destructive.
Absolutely. The strong winds push the ocean water toward the shore, generating a massive storm surge, a devastating wall of water that can be anywhere from 3 to 12 meters high.
Flooding everything.
Flooding coastal regions, contaminating drinking water, and the salt water reduces soil fertility for years. The after effects are often worse than the initial wind damage.
Which is why weather monitoring is such a high-stakes endeavor.
Absolutely. Agencies like the India Meteorological Department use dedicated satellites to constantly track and predict the paths of these massive pressure systems. Mitigation relies entirely on preparedness.
Knowing the path gives communities time
to prepare emergency kits and move to designated cyclone shelters. Understanding pressure is, quite literally, about saving lives.
We've covered a remarkable distance in this deep dive. We moved from the simple principle of distributing a heavy force with broad straps to understanding why a 225-kilogram column of air doesn't crush us, and how that same need for equilibrium generates wind speeds of 270 kilometers per hour through heat, condensation, and the Earth's rotation.
What's fascinating here is that the seemingly simple concept of pressure, just the constant drive for air to move from high density to low density, is the fundamental engine of global weather. Every little breath of wind, every massive storm system is just air moving to balance the scales.
So for our final thought for you to ponder, considering that high-speed winds result in lowered pressure and that a dam's base is brought in to resist extreme outward pressure, why is the eye of the cyclone, the region of lowest pressure and most aggressive spin, paradoxically the calmest part of the storm? The forces are all there, but at the very heart of the chaos, the pressure gradient force pulling air inward is perfectly balanced by the outward centrifugal force created by the rotation. It's a temporary, perfect physics solution right at the center of the storm. Something to ponder as you look up and feel the weight of the sky.